All right, we are on page 7 of going over the final exam review packet. And for number 52, it says figure out how many grams you need to make these solutions. Well, it's helpful to think back to your molarity triangle and think about which of these is most closely related to grams. Well, if you know moles, you know grams because all you have to do is multiply by the molar mass. So for letter A, if we can figure out the molarity and then multiply it by how many liters we're going to need, we can figure out how many moles of potassium hydroxide and then convert to grams. So let's do that. If I divide 2,500 milliliters by 1,000, I get 2.5 liters times 3 moles per liter. That's the concentration I want to make. That means I'm going to need 7.5 moles of KOH to make my solution. Well, I can easily calculate how much 1 mole of KOH, how much that weighs. That's 56.11 grams if you add that up. So then multiply by 7.5 moles, you're going to need 420.83 grams of KOH. So you can picture this, it's a white substance. You mass this out on the scale, throw it in 2.5 liters, and you've got 3 moles per liter. That's the concentration. Okay, similarly for 52b, if we take 2 liters times 2 moles per liter, we're going to need 4 moles of HNO3 to make this particular concentration. So how much does 1 mole of HNO3 weigh? If you add it up, it adds to 63.02 grams. Multiply that by 4, you're going to need 252.08 grams of HNO3 to make your solution. 53, explain how intermolecular forces, really this is saying how does polarity, which also ultimately affects the intermolecular forces, influence how things are going to dissolve in each other. This is getting at that whole rule where like dissolves like. So let's look at an example. Would iodine crystals dissolve in H2O? H2O is extremely polar. This oxygen is pulling an electron cloud from both of these hydrogens. Very polar. This is a tie, so this is nonpolar. So are these alike? No. Would iodine dissolve in water? No. What about something like NH3? Would this dissolve in water? This is also extremely polar, so yes, it would. Also, ionic things dissolve in water, like NaCl. They get pulled apart. All right, 54, switching gears. Calculate the molarity. So we need to know moles per liter of this particular solution. It says we dumped 212.5 grams of NaNO3 into 3 liters. So first we need to divide by NaNO3's molar mass, which is 85.01. We put 2.5 moles of it into 3 liters. Moles per liter will tell us the molarity. This comes out to be 0.83 molar sodium nitrate. What about dilutions? Anytime you see a problem like 55 where it says you've got a stock solution and you want to know how much of this you need to use to create the solution you want, you should think about the formula M1 times V1 equals M2 times V2. So you want a 2 molar solution. You don't know how much volume of that you should use to make a 0.75 molar solution, and you definitely want 300 milliliters of it. So solve for the unknown by dividing both sides by 2, and you're going to need 112.5 milliliters. But what the heck does that mean really? So I'm going to go off to the side. Here's your stock solution. It's really concentrated. You've got a bunch of it. And then you've got a 300 milliliter volumetric flask. There's the line. What this is saying is you need to measure out 112.5 milliliters of that super concentrated stuff Okay, so here it is. And then you're going to fill to the line with just plain old water and mix this up. And those little solute molecules here are going to spread out and they're going to be weaker. It's only going to be a 0.75 molar solution now rather than a 2 molar. 56 is the same with a little twist. It says, okay, you've already got this solution and how much water do you need to add? So you're diluting, let me write this out again. You're diluting a 6 molar solution, 1 liter of it. You're diluting it to a 5.5 molar solution. So first let's figure out the total volume that your new solution is. It comes out to be 12 liters or 1200 milliliters. So if you started off with 1 liter, sorry, I should make this a 12 liters. If you already started off with 1 liter, then how much water do you need to add to make it 12 liters? You only need to add 11 liters. 57, what are some things that speed up or slow down a chemical reaction? So temperature is one. If you heat up a solvent, it's going to have molecules moving much faster in it, and you'll be able to either react or, this is chemical reaction, you'll react with your solute much faster. Or the opposite, if you cool something down, your reaction is going to slow down because the molecules are moving slower. How about concentration? If you've got a solvent that is really concentrated, it's going to react a lot faster because there's more to react with. Surface area. If you throw a big, I'll use a dissolving example for this one. If you throw a big block of salt into a swimming pool, it'll dissolve, but it's going to take a while. The water molecules are colliding with the sides of the block, and they'll eventually get to the ones in the center. But if you crush up that salt so that it's just little individual grains and you throw them all at once into the pool, they're going to dissolve immediately because there's a really high surface area. Finally, catalysts are chemicals that can speed up a reaction. Equilibrium. Remember I talked about how I've been lying to you all year, and reactions can actually be reversible. So what does equilibrium mean? This is when you've reached a place where the wrong one. The rates of the forward and reverse reactions are equal. So the rate at which reactants are turning into products is equal to the rate at which products are turning into reactants. So let's look at an example. This is supposed to be a reversible arrow here. I'm not sure why it's not showing up. It says, basically figure out which of these would increase the amount of SO3 being formed. So let's think about some different possibilities here. For A, it's increasing the pressure. Notice that the left side has 2 gases and the right side only has 1. So this side is going to be way more affected by an increase in pressure. These particles are going to start colliding a lot faster and more, and it's going to shift the whole equilibrium to the right, and you're going to make more SO3, which is why A is the correct answer. But why are the other ones wrong? Well, decreasing the pressure is just the opposite. If you decrease the pressure, these aren't going to collide as often, and it's actually going to do the opposite. The SO3 is going to want to try to make more of these gases because it's going to say, what the heck? Why are these things not being produced more? Because usually it's used to the rates being equal. So increasing the temperature, the side that the heat is on is here. So if all of a sudden you increase the temperature, it's going to want to shift the equilibrium to the left to try and get rid of some of that excess heat. Or if you remove some oxygen, this side is going to say, oh my gosh, we need to make more oxygen. We're running out. So that would also shift the equilibrium to the left, which is not what the question was asking. 60 and 61 is review what are some properties of acids. It's important to remember the pH scale. Things that have a pH less than 7 are acidic. Acids are things that start with an H typically. They add H plus to solution. Bases are things that have a pH greater than 14, and they form hydroxide ions in solution, either from their own formula or bases accept hydrogen. So there's the bad to remember. Bases accept, acids donate hydrogens. Okay, and there's other things too, like acids are sour, bases are bitter, they're both corrosive. So those are all other properties you can consider.